Hello everyone. Today we are going to be taking some notes on section 1.5. So I'm going to go ahead and start that now. I may have to pause my recording a little bit later and then pick up just because of time right now on my plan, but I will definitely get through this in maybe two parts. So today we're going to be talking about how to solve quadratics by finding square roots. But before that, there is a warm-up here. You might want to go ahead and try this warm-up. So again, at any time in this video, definitely want to hit pause, maybe to try a problem and just to see how I work through it. This would be a great example here to go ahead and just try it in your notebook. You don't have to do it on a whiteboard, or you can, but making sure that you know how to solve this equation by factoring. You do have a nice touch screen, so you could touch screen pause and touch screen play pretty easily without being too much of a hassle. So I'm going to go ahead and work through this quietly just to see. You could keep it going and then kind of look up at the screen if it gets too far and pause it. I'm just showing here kind of how you can think about it. I know it's kind of weird when I write it out, but I'm trying to help you figure out what factors to try, or you can just try the ones at the bottom and then guess and check with those. Remember the problem that I asked you to solve? So solve means to find the solutions that would make the left side of 6x squared minus 7x equal the right side of 5. So there are two answers that would do that. So make sure you're finding those answers correctly. Okay, so 1.5, as I mentioned, solving quadratics by finding square roots. So we're going to do that. We've been solving quadratics by factoring, and there are different ways of solving quadratics. The first way that we usually use is factoring, but square roots is a really quick way to solve if we just recognize when to use square roots. Identifying things in word problems and interpreting the context of the solution, we've had that going on a few times there. So first thing we're going to do is we're going to review properties of square roots. You have two properties of square roots that you learned back in Algebra 1. So we're going to look at example 1 below. That's what that's saying. The product property is whenever you have the square root of two things being multiplied together, such as the square root of 4 times 3. So it might have started to be the square root of 12, but we're going to break it down into perfect square factors. So maybe it's the square root of 4 times the square root of 3 is how I could break it down. And then the quotient property, that's our second one. And that's telling us that if I have the square root of a fraction, then again, I can take the radical of the numerator and the radical of the denominator. And we're going to see that in 1c, 1d, and then also 2a below. So kind of looking at those examples here. So you might need to take a moment to pause that so you can get those written down, and I'm going to go ahead and move on. So example 1 is just reviewing Algebra 1 stuff because we didn't use it a ton in Algebra 1. You might use it again in geometry, but we used to use it in geometry. I'm not sure if you do anymore. Hopefully you do, but simplifying these expressions. So the simplify, that's our key word here. We're trying to get it as simple as we possibly can. So we're starting here with the square root of 80. So just write down one at a time here for me. So we want to start thinking about our perfect square factors. So since I'm not with you, we list them out. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so forth. So you should know these probably up to 12. I'll go up to 10, we're running out of room there. What we want to do is we want to figure out the biggest perfect square factor that goes into 80. And you can use your calculator, it would actually be 16. So this will be the square root of 16 times 5. I like to write my perfect square first. okay? And so then I would break that down to the square root of 16 times the square root of 5, and we would get 4 square roots of 5. If you're thinking, you know, I need another way to do this, you can also go back to when we were factoring and you could list out factors of 80. 3 wouldn't work. 4 times 20, 5 times, what would be 16? 6 wouldn't work, 7 would work, 8 times 10, 9 would work. So if we're looking here, you start with the biggest one, and you start working down and back around, and you try to find what's the biggest factor of 80. That would be a perfect square, and that would be 16. Notice 4 is also 1, but it's not the biggest one. So that's another way you could think about it. On the second example, what we have going on here is we have a product of 2 radicals, but neither of these are perfect squares. So the first thing we have to do is we have to apply our rule that we can actually multiply them together. So when I multiply 6 times 21, I get the square root of 126. And then I want to try to break it down. And I didn't list out all my factors, but again, you could think 1 and 126. 2 would be 63. 3 would be 42. 4 wouldn't work. 5 wouldn't work. 6 would work. 6 times 21. 7 wouldn't work. 8 wouldn't work. 9 would work. 9 times 14. No 10, no 11, no 12. So again, starting from the back, none of these are perfect squares until I get right here. 9's the biggest perfect square. So I always write my perfect square first. So it'd be the square root of 9 times 14. I can break those apart. You'll get to where you don't even have to write them. Either the square root of 9 times 14, or maybe you even see it. But it is the square root of 9 times the square root of 14. The square root of 9 is the one that comes out of the perfect square, or the radical, excuse me, because it's a perfect square. And as I'm talking, I write 15 instead of 14, but then it would be 3 square roots of 14. Again, 14 only has factors of 1 and 14, 2 and 7. I don't need to take the square root of 1, it's just 1, so it doesn't help me any. So that would just be simplifying them based upon the product property. The next one is trying to do it with the quotient property. So the quotient property, you see here, the square root of 4 over 81. All the quotient property is saying is that I can give the numerator and the denominator both a square root. The square root of 4 is a perfect square. The square root of 81 is a perfect square. So we end up getting it simplified to be 2 over 9. Now the last example we have here is the square root of 7/16. And we want to make sure, as we're doing this, that we have the denominator rationalized. So that's what that's saying. Okay, we're going to talk about that in a moment, because not all the time is it going to be like this. So if we follow the same strategy as we did in part C, we would take the square root of 7 over the square root of 16. Well, the square root of 7, I only have 1 and 7, so it's not going to simplify any. It's going to stay the square root of 7. The square root of 16 is a perfect square, so it's going to stay 4. When we say we have to rationalize the denominator, that means that the denominator, the bottom part, must be a rational number. The square root of 7 is irrational, but 4 is rational. Okay, any integer that we have, that would be rational. Okay, so all of our integers are what we're looking for there, to be rationalizing the denominator. Okay, so we're going to focus on that. So the next thing that we see talks about what happens if we're trying to rationalize a denominator, what does it really mean? So I kind of mentioned this, but what it does, it eliminates radicals in our denominator. And it is required for something to be simplified. So if we're asked to simplify something, you definitely have to rationalize the denominator. We're going to use what are called conjugates to help us do that. So this is kind of new to us, but we're going to use this later in the chapter as well. But conjugates are terms whose product is always a rational number. And there's some ways we want to look at these. Like if we have two things added together, A plus B, we want to think of A minus B. Because remember, if we multiplied those two things together, it would be difference of squares. That's kind of where this is coming from. Okay, and I'm going to show you what that looks like in an example. So for right now, just stick with me there. It's the same first term, the same last term. There's just a different sign in between the two terms. Okay, the other thing that I want to mention here is that we would use parentheses and we would distribute, so that would be important. But we're definitely going to come back to it here. So if you're still writing this, definitely want to pause it. Again, I'm going to go on for purposes. I'm going to have about 5 or 6 more minutes here before I'm going to have to pause it for good, and then come back to you. But I want to go ahead and try to get through another example or two here. So the next one we have here, hopefully you pause that, is we're going to look at this first one. Sorry, I'm using a loaner computer, so I'm not quite used to it. Whoa. The square root of 5 over 12. So we want to write that down, the square root of 5/12. So I think I can make it through this one, and then I'll come back on here in a little bit. So here we're going to have the square root of 5 over the square root of 12. The square root of 5 doesn't simplify any, so it's going to say the square root of 5. We don't have a perfect square other than 1. But if we think about the square root of 12, we can try to think about a perfect square that comes out of 12. So hopefully we're thinking about 4. So I'm going to go ahead and just break those apart. So we have radical 4 and radical 3. Well, radical 4 is the perfect square. It becomes 2. So we end up with 2 radical 3. However, this is not rationalized because our denominator still has a rational number. So we go back up to our definition that eliminates radicals in our denominator. It is required if we say to simplify. So I no longer want to have radical 3 in our denominator. So what we're going to do is we're going to multiply by something that's equal to 1. And the way that we're going to get that something is we're going to look at the denominator, and we're going to pick up the radical. So I'm going to multiply the denominator by radical 3, and then I have to multiply the numerator by the same thing, because this fraction right here is equal to 1. And I can always multiply a fraction by 1 without changing its value. Now, when I do that, we have to apply our rules. So radical 5 times radical 3, we would multiply those because they're both under a radical. That gives us radical 15. We do the same thing at the bottom. The 2 would stay outside the radical because it's already outside. We would take 3 times 3 and we would get 9. However, right now we should recognize that 9 is the number 3. So what we have here is we have 2 times 3 in our denominator. Well, that's rational now. 2 times 3 is 6. Square root of 15 in the numerator, I only have 1 and 15, 3 and 5. So there are no perfect squares other than 1. So the square root of 15 would remain. You can have a radical in the numerator. You just cannot have a radical in the denominator for it to be rational. So I'm going to pause my video now, and I'll be back on in just a little bit. Okay, so we're back. Hopefully this is working like we expect it to. So remember what we're doing is we are working to simplify these expressions. So we were working with the square root of 5 over 12, or the square root of 5/12. Remember that in order to simplify these, we need to rationalize the denominator. So we have to eliminate the radicals. So the second one that we have is a little different. It's 3 divided by 7 plus the square root of 2. Now, the reason this one is different than the one before is because the one before just had one term in the denominator. You'll notice that it has just the square root of 12. That would be considered a monomial, one term. However, for part B, we have a binomial. It's 2 terms. It's 7 plus radical 2. So if we were to multiply just by a monomial, like radical 2, we would still have a radical in our denominator. So we can't do that. So that's where the second thing that we were talking about up here applies. We have to use a conjugate. We have to use the idea of the difference of perfect squares when we factor. So we have to do something in the form a plus b and a minus b. So we look down here, this is in the form a plus b in our denominator. So think of this as a plus b. So we want to multiply it by something that would be a minus b. That would be the conjugate. And again, we're worried about the denominator. The numerator can have radicals. It's the denominator. So we're going to multiply this by 7 minus the square root of 2. So really the only thing that changes is the sign between the 2 terms. So if this would have been 7 minus radical 2 to start with, we would have done 7 plus radical 2. So that's what we're trying to do here. And again, whatever we do in the denominator, we also have to do in the numerator because that is equivalent to 1. Now, what we're going to do is we're going to make sure we distribute since we have a binomial. So I'm going to put that in parentheses because I want to make sure that I'm distributing what I have here. So we're going to have 3 times 7, 21, and then 3 times negative radical 2. So minus 3 radical 2. That's our numerator. In our denominator, not only is 7 minus radical 2 in parentheses, but so is 7 plus radical 2. So as we multiply, 7 times 7, 49. 7 times negative radical 2 would be negative 7 radical 2. Remember, outside stays inside, inside stays inside. The first terms here, I did that one backwards. Sorry, I hit the wrong thing there. We would do, whoa. Let's go back. My smart board is a little off. Okay. Should be back at it. Yes. Maybe I should orient my smart board to help us out. Okay, we're back at it. So here we go. Radical 2 times 7. So plus 7 radical 2. And then radical 2 times negative radical 2. So that would be negative square root of 4. They're both under the radical. So it's going to end up being 2 times 2, which is the square root of 4. Now, as we look at this, what we see is the minus radical 2 plus radical 2 in our denominator is going to cancel. And here, radical 4 is just 2. So this is going to be minus 2 because it was negative square root of 4. So we're going to have 21 minus 3. Oh, our smart board's doing that funny thing. Try again. So 21 minus 3 radical 2 all over 49 minus 2, which is 47. Okay, that's going to be our answer. Trying to get an equal sign there. That would be our answer for that particular one. So again, when you have a binomial in your denominator, you're going to multiply by its conjugate, which is the idea of the difference of squares. And notice, since the radical 2's canceled out, and then we ended up with radical 4, that became a perfect square, so we were able to simplify it down with a rational number. So 47 is rational. Okay, so what we've done is we've really just tried to talk about how to simplify radicals. We haven't even gotten to our objective. We were kind of doing some stuff that we did in Algebra 1, and then also a little bit of new stuff with the rationalizing. We're going to get here to where we're solving. So we are going to try to solve 3x squared plus 5 equal to 41. I'm going to say that again because I'm going to orient this. So 3x squared plus 5 equals 41. Three x squared plus 5 equals to 41. Okay, sorry about that annoyance. So here we're trying to solve. So remember, to solve means to find the value of x. So what value would this x have to be to where we would get answers here? Now it is squared, so remember, quadratics make parabolas. So it's likely that we're going to have 2 answers because it is a quadratic, has a degree of 2. So what I notice here is I notice when I look at the whole problem that I don't have an x. Hopefully you notice that you don't have a b term. Okay, the 3 would be considered a, but the 5 and the 41, if we subtracted 41, we'd get minus 36. Okay, that would be our c value. So when I don't have a b value, there's no b value in my problem, meaning that I don't have anything like 3x, negative 5x, 7x, anything with just an x, then I can use this process called square roots. So what I want to do is I want to try to get my x squared by itself, whatever is being squared. Okay, here in a little while, we're going to have like a quantity of x minus 3 squared. That's still considered to be a quadratic, so that would not, shouldn't have put it in that category, but that would not fall in the category of a b value. Okay, and you'll see that here in a moment. So what we're going to do is we're going to try to isolate the x squared. So hopefully you're recognizing that we can subtract 5. Still, if I want to get x squared alone, I'm going to have to divide by 3. So we get x squared to equal 12. Now, what do you think we're going to do in order to get x by itself? Hopefully you're thinking we're going to take the square root, and that is exactly what we're going to do. Now, when we do that, there's something that we have to pay attention to. We do get the square root of 12, but not only do we get the positive square root of 12, we also get the negative square root of 12. So you might recall doing that in Algebra 1 where we were solving and you would get plus or minus a number. Let me explain why. If we went over here and I said x squared equal to 9, it's a little easier to do it with a perfect square. If I were to take the square root of both sides,
if I just said x equal to 3, that is true, because 3 squared is 9. But it's also true that negative 3, if I square negative 3 times negative 3, it is also 9. So if you go back to the equation x squared equals 9, this x could be positive 3 or negative 3. So we can just say plus or minus 3 from the very beginning. That's kind of the idea of what we're doing here. Now, going back to what we just practiced, we have to simplify. So if I think about factors of 12, I want to try to take the biggest perfect square. So if I'm working around, the biggest perfect square is 4. So it would be square root of 4 times the square root of 3, which would be 2 radical 3. That would be my simplified answer. So plus or minus there. Now, some of you might have noticed there are a couple calculators out there that will do that for you. If yours is one of those where it simplifies the radical for you, you will not be allowed to use it on a quiz or a test. So you need to make sure that you understand how to simplify that radical without a calculator, so not just typing it in. Okay. Now you could get the decimal approximation, so you could take 2 times radical 3, get a decimal for that, take square root of 12, get a decimal for that. It'd be like around 3.5, and they should match. And that would tell you that you simplified it correctly. Okay, let's look at another one that has the quantity like I mentioned. In this case, this quantity of x plus 3, that is not considered to be the b value because it's being squared. So what I want to do here is, because I have this quantity squared, okay, think about it as just like even, 1/5 times happy face squared equal to 7. I mean, even think of it like that. If I can get whatever is squared by itself, then I can use square root. So if I can get this part by itself, then I could use a square root here. So what we want to do is we want to get rid of the 1/5. Now you can divide by 1/5, and if you do that, you want to make sure you're putting the 1/5 in parentheses. So that is one option that you have in order to solve this. Okay, we typically don't do that whenever we have a fraction we want to divide. Maybe you remember, but we're going to actually multiply. Whoops. We're going to multiply by the reciprocal. So that's what we want to do instead. So we want to multiply both sides by 5/1 because that's the reciprocal. Again, if you multiply or divide, by 1/5 with parentheses or using your fraction button, you're going to be fine. So the idea is that 1/5 times 5/1, if you multiply straight across, would give you 5/5, which is 1. So these cancel. We're left with z plus 3, quantity squared, and then 7 times 5 is 35, divided by 1 stays 35. Now, I have a quantity being squared, it's all by itself. So how do we get rid of it? We take the square root. When we take the square root, we're left with z plus 3. But on the right side, because I took a square root, we have to remember that it's plus or minus the square root of 35. Not just the square root of 35, plus or minus the square root of 35. Okay? So from here, what we want to do is we have to get z alone. Let's try to simplify radical 35 first, though. So I think 1 and 35, 5 and 7. Are any of those perfect squares? And if we went through, they would not be. Okay, 1 is the biggest perfect square, and that's not going to change anything. So all we're going to do is subtract 3. Now, when we subtract 3, 3 is outside of the radical. So you cannot subtract 3 from 35. It's the square root of 35. So we're just going to write it in front, negative 3 plus or minus the square root of 35. And that's going to be our answer. If we were trying to figure out what those would be, we had to find approximations and word problems, which we will have to do. This would be like negative 3 plus the square root of 35 and negative 3 minus the square root of 35. And we could type those into our calculator and we could get an answer. So it would be somewhere close to 6, like 5.9, and then somewhere almost to negative 9. So negative 8.9 or something like that is what we would get. So that's how we would do it. So what we're doing here, guys, is we're kind of doing order of operations in reverse from the very get-go. We would always do parentheses and exponents last here because typically those are done first. So since we have that quantity, we're going to leave it till the end. Okay, think about doing order of operations in reverse. So we're going to add or subtract if we can, outside of a parenthesis or an exponent. Then we're going to multiply or divide if we can, which we could. We got rid of the 1/5. Then we're going to get rid of the exponent, which is taking the square root, and then we're going to get rid of the parentheses and subtract that 3. So that's what we would get there. Okay? So the last one. The last one gets into why in the world do we do this? And that is because there is something going on in the real world that has to do with parabolas. We've seen it a little bit when it comes to price or revenue and the number of items. We've seen it when it comes to the shape of a bridge, possibly a suspension bridge, or the arches. Okay, this is what happens if we're dropping an object. So you definitely want to get this equation in your notes. You will need to know it. So h equals negative 16 t squared plus h sub 0 is what that is. So h stands for the height in feet. And what I mean by height, I mean the final height, okay, the ending height. Okay, so what do we end up with? What's our final height that we get? Okay, t is going to represent time, and it's going to be in seconds. When you take physics, it might be in meters. It would be a different number there. It would be negative 9.8. But that negative 16 is talking about gravity. Gravity is 16 feet per second squared is what it does to objects as far as moving them on Earth. And then h sub 0 would be the initial height of the object. So I have to know the initial height, it gets affected by gravity, and it gives me my final height. That's what this is saying. Later we'll talk about what happens if we throw an object, like a football, or we kick a soccer ball, or let's say we spike a volleyball. We'll talk about all those. Okay, so taking that equation, we're going to use it. So, for a science competition, students must design a container that prevents an egg from breaking when it's dropped from a height of 50. How long does a container take to hit the ground? If we want to know how long it takes to hit the ground, we want to know time. How long would be how much time? And in this formula, in this equation, time is t. That's what we do not know. That means if we don't know time, we better know height, okay, that we're going to end with, and we better know the initial height that we start with. Because we only have one equation here. So if we only have one equation, we can only have one thing we don't know, and that's time. Okay, the easy one is where we start. It's dropped from a height of 50. You see this guy here? He's dropping this egg from 50 feet above the ground. Okay, that's h. So h is 50. Okay, we also know, how about not h? That's not the initial height. The initial height, sorry, h sub 0 is what I meant to say. Okay, we know the initial height where it starts. We know that's 50. I'll get the right pen here in a moment. Okay, so we know it starts, excuse me. Yeah, it's starting. He's starting up here. He's starting from an initial height, h sub 0 of 50. The harder one to come up with, we don't think about it, don't make it too hard here, is what's our final height? Well, it tells us. It tells us we want to hit the ground. If we want to hit the ground, we are on the ground. So what height above the ground will we be? Hopefully you're thinking 0. Okay, because that's the right answer. We would be, if we're hitting the ground, we are 0 feet above the ground. Let's say that he dropped this egg and ended up on this table. And let's say the table was 4 feet above the ground. Then our h value would be 4. Okay, but he's going to go all the way to the ground here. So we're going to take that information and we're going to sub it in. So we know our final height is 0, negative 16t squared. Our initial height is 50. So that's just like a couple examples ago where we solved that equation. We're trying to solve for time. So notice again, there's no b term. There's just something squared. So we're going to subtract 50. So negative 50 equals negative 16t squared. Again, we want to get t squared alone. So hopefully you're seeing that we're going to divide by negative 16. You could use your calculator and take negative 50 divided by negative 16. I'm just going to leave it that way. Because since this is a word problem, we are going to get a decimal approximation. Our next thing would be to take the square root. Recognize that two negatives would make a positive. So whenever we take the square root of that, we are going to get that t is approximately plus or minus, remember, 1.77. Again, you took a square root. Remember, that has to be plus or minus. Okay, don't forget to put that on there. It's a quadratic. Exponent of 2 means 2 possible answers. But do those answers really make sense? Okay, did it take negative 1.77 seconds to drop it? No. So we know that the answer to our problem is just 1.77 seconds. That's the approximate amount of time that it took to drop that egg. So today, again, what you're practicing is you're practicing how to solve a quadratic using these square roots. So you should not have to multiply it to standard form. Okay, recognize that you have something squared but you don't have a variable by itself. And probably the hardest one to see that on is here. You still have a quantity here being squared. So I want you to try to recognize that quantity being squared there means we're going to save it till the end and use those square roots. It's going to be a very, very easy way to solve. So your homework today is 1.5. So you want to make sure you have that ready to go for the next time I see you, which would be Monday. And if you have any questions, I'll be able to be here Monday morning and answer any questions, or I will actually be here today after school. And you can also send me an email, ask a table partner, ask someone else in the room, or we can take a couple before we grade our homework. So have a great day. Have a great weekend.